Okay, so in this chapter we'll study sound waves. Sound waves are, well, you have a sensor for sound waves. These are mechanical waves. These are waves that need a medium to travel in. They won't travel in vacuum. Okay. And you have a sensor that can hear sound waves coming through fluids, traveling through fluids. Air is a fluid. Okay. It turns out that sound waves, only longitudinal waves can travel through fluids. Okay, so through fluids, which is liquids and gases, you can have only longitudinal waves. Through solids, you can have both transverse and longitudinal waves. All right, so let me start off by showing you an example. Where Okay. So what you can do is you can take any object, it can be a physics book or whatever, and make it and wave it back and forth. Okay. And what this will do is it'll create sound waves. Okay. So this is illustrating a diaphragm in a cylinder. Okay. And as you wave this back and forth, it creates sound waves that have the same frequency as the frequency of oscillation of this object. Okay. Now it turns out that so you can, in principle, create a sound wave of any frequency. Okay. Whatever frequency this thing you oscillate it with, that's the frequency of the sound. Now your sensor happens to, this sensor that you have works only between 20 hertz and 20,000 hertz. Okay. But you can create a sound of any frequency. Okay. So sound of frequency below 20 hertz, those are called infrasonic waves. And sound of frequency higher than 20,000 hertz, they're called ultrasonic waves. And in fact, in a lab, we use a sensor instrument that produces sound waves of frequency higher than that, 20,000 hertz. Okay. Bats use higher frequencies. Elephants, for instance, use low-frequency sounds, okay, less than 20 hertz. They use infrasonic sound waves. Do you know why they might use that? It turns out low-frequency sound waves can travel further. Okay, and elephants are vegetarian, they gotta eat a lot, so they gotta be familiar with a large grazing ground, and that's useful for communication. Okay, so to produce a sound wave, you need a source that pumps energy into the medium. So this oscillates, and you see a longitudinal wave is where each particle of the medium, that red dot, is oscillating parallel to the direction of wave travel. The sound wave, you can think of it, see, when it goes to when the object is going to the right, it creates a compression, and then there's a partial vacuum or rarefaction. So the sound wave is a compression and a rarefaction. Okay, so if you measure the pressure here is higher, the pressure there is lower, and so on. Okay, so let me show that to you. Okay, so you saw that when a speaker, the diaphragm of the speaker goes back and forth, it creates, this is a high pressure region, low pressure, high pressure, low pressure, and so on. Okay, so you can represent this sound wave as a pressure wave. Okay. And so if you could watch each air molecule, so as this diaphragm oscillates back and forth, you're creating a high pressure region, low pressure region, high pressure region. So there's the pressure, there's the high pressure region, low pressure region. So here's a pressure wave that's traveling to the right. And in one of the previous chapters, you learned how to represent this mathematically. There it is, okay? So there's the pressure wave, the pressure at location X at time t. There's the amplitude of the pressure. So this is the amplitude of the pressure, okay? There's the wave number. Remember, this thing is related to the wavelength of the wave. And omega is the frequency of the wave, which is related to the frequency at which this oscillator is producing the sound wave. Okay? And which direction is this wave traveling? To the right. Okay? So the sound wave is a pressure wave that is traveling. So this in fluids, it's a longitudinal wave that's traveling to the right. When a wave travels in a medium, is the medium transported? No. And you see that in this simulation, okay? So you can see that in this simulation, the air molecules themselves are not translated. Okay, they oscillate back and forth. Now here's the deal. You can take a book and wave it back and forth. So you're pumping energy into this medium. It turns out that, and so when a speaker, the diaphragm vibrates back and forth, it turns out that about 99% of the energy that this thing is pumping in, it turns into heat. Only about 1% is converted to the sound. Okay? So almost a small part of the energy goes into compressing and expanding the surrounding area. So if you have a 100-watt speaker, it's using 100 joules of energy, electrical energy per second. Only 1 watt of that is being produced, goes into sound production. Okay? So sound waves in fluids are longitudinal because fluids have no shear strength. In solids, sound waves can be both transverse and longitudinal. Okay, so when I'm banging this table, I've set up both longitudinal and transverse waves on this side. Okay, but when I'm talking, only longitudinal waves are reaching you guys. Okay. All right. So here's a pressure wave traveling. Okay, here's one more thing I want to point out. Okay, what this is giving you is the motion of the gas particles. Okay, so that equation refers to that red dot. Okay, that's a gas molecule that's oscillating back and forth like that. Okay, and so what we'll do is we'll explain how this high pressure and these low pressure regions arise. Okay. So again, this is a snapshot of this situation. Well, how did this high pressure arise? Okay, what this graph is saying is the molecules that were here are at rest. These molecules have a positive amplitude. So these molecules are are over there now at this second. And these molecules have a negative motion. So these guys are over there. So that's how you have a high pressure region. Okay, in this snapshot, these guys are at rest. These guys are located over there. These guys are located over there. Okay, that's what this graph is telling you. Okay, so anyway, the molecular motion and the pressure waves you see are 90 degrees out of phase. Okay, anyway, this is just a technical difference. Don't worry about it. So think of the sound wave as a pressure wave. And in a fluid, it's only longitudinal waves that propagate. Okay, the amplitude of the pressure wave is given by, that's the density of the fluid, that's the velocity of the sound wave, that is the frequency of the sound wave. Okay, and where is the frequency coming from? That's the frequency at which you're oscillating vibrating the oscillator. And this is the amplitude of the air molecules. Okay. Greater the amplitude of the air molecules, greater the pressure amplitude of the pressure wave. Okay, so again, sound waves are mechanical waves. So in fluids, there are only longitudinal waves. They need a material medium to travel in. Okay, so you can't have sound waves in vacuum. Their speed depends on the properties of the medium. Okay, so you'll see that in stiffer medium, sound waves will travel faster. Okay. All right, now we'll talk about wave fronts. So let me show you. Okay, so wave fronts are crests created at the same time. So these are circular wave fronts. Okay, so what this is this is a ripple tank. You can think of a mass attached to a spring that's oscillating and hitting the water, and it's creating these waves. So the wave fronts are these circular wave fronts. Okay, why do you think we're talking about wave fronts? What significance could they have? What do waves do? What kind of stuff do they carry? I'm sorry? They carry energy. Okay, and you ask what is the direction in which energy is propagating? Energy is propagating perpendicular to the wavefront. Okay, so energy travels perpendicular to the wavefront. And okay, so energy travels perpendicular to the wavefront, and along the wavefront, for a given wavefront, this quantity is the phase. On a wavefront, the phase is the same all along the wavefront. Okay. So if a source is very far away, you can have plane wavefronts. When a bird sings, you have spherical wavefronts. Okay. And you go to the beach, those waves were created a long distance ago. You have a linear wavefront. Okay. And so on. So you can, the sensor you're born with is, you can hear between 20 and 20,000 hertz. Okay. Now, generally, it turns out that as you get older, I probably can't hear about 7 to 8,000 hertz. A lot of the younger people, a lot of you guys probably can hear 14, 15,000 and higher frequencies. Okay. So teenagers can hear frequencies over 10,000 hertz. I might have mentioned this. Did you guys do in high school, did you guys have these high frequency ringtones, which the teacher couldn't hear, but students could hear? Okay. So you've done that? Okay. So some businesses use that in reverse. If you go to a mall, an expensive mall, and there are expensive stores, and if they want to keep the teenagers out, what they'll do is they'll play a high-pitched sound which teenagers find annoying, and the older customers can't hear it. So they can use it both ways. So back in the day, by the way, when bandwidth was expensive, telephone companies only used these frequency ranges to transmit your telephone calls. But nowadays, bandwidth is cheap, so you can use you can transmit a higher range. Okay, so these are infrasonic waves. These are ultrasonic waves. Okay? So there are all kinds of systems that use, so bats use ultrasonic waves, sonars use ultrasonic waves. Okay. Loudness, so we'll talk about loudness, and so we can hear in this range. This is the range of our hearing, okay? And you see, for low frequency, the sound has to be quite loud before you can hear it. It turns out that your ears are most sensitive to this frequency, which is about 3,500 hertz, okay? And so on. So your perception of loudness depends on frequency as well. Okay, we'll talk about that. So infrasonic waves are sound waves of frequency below 20 hertz. Ultrasonic waves are about 20,000 hertz. Okay. Okay, so it turns out that the speed of sound waves depends on the elastic property of a medium and the inertial property of a medium. Okay, so the stiffer the material, bigger this number will be, faster sound will travel. Okay. Okay, so for longitudinal sound waves, the elastic property that's relevant is the bulk modulus, okay, and the inertial property is the density of the medium. Okay, so that's the speed of sound for longitudinal waves. For transverse waves, that would be the shear modulus, but we'll generally deal with only longitudinal waves. Okay, so longitudinal waves traveling in solids, liquids, or gases, this is the formula. Okay. So let's look at, you mostly get sound waves traveling through air. Okay. Now, if you happen to be a scuba diver and live underwater quite a bit, then the sound wave is traveling to you in water. But okay, so in air, the speed of sound is about 340 meters per second. Okay. We'll measure this in lab in physics too. Okay. So let's say in water, the speed of sound is 1,500 meters per second. It's about 5 times faster than in air. In iron, it's about 6,000 meters per second, which is about 20 times faster than in air. Okay? So you can see that it turns out that the speed of sound in air depends on the temperature of air. So this formula gives you the speed of sound as a function of temperature. So here's the speed of sound. There is the temperature in the Kelvin scale. R is the gas constant. Gamma is the ratio of specific heats, which we'll learn about in physics too. Gamma is Cp by Cv. Okay, so this is and gamma tells you the complexity of the molecules that the gas is made of. So for instance, air is made of diatomic molecules, nitrogen and oxygen. Okay, so for monoatomic gases, this number is 1.67. For diatomic gases, it's about 1.4. And for more complex gases, the number is smaller. Okay, so it's a ratio of specific heats. Okay, so for air, this is 1.4. Anyway, here is the speed of sound as a function of temperature. This is in Kelvin scale, this is in Celsius scale. Okay, for at 0 degrees Celsius, the speed of sound is 331 meters per second. Okay, and for every degree rise in temperature, the speed of sound increases by 6.6 meters per second. Okay. Why do we care about this? You guys might have gone to a concert, and if the playing hall is cold or something like that, so for instance, if you have a flute, okay, that you're playing, the wavelength that you're playing depends on the length of the flute. That's not changing. Okay, and so the speed of sound is frequency times the wavelength. And if the speed of sound changes with temperature, a given length of flute will produce a different pitch. So they have to tune it appropriately. Okay, and sometimes they'll even warm the flute or warming the air inside it. Okay, so Anyway, so you might have seen the effects of that in a concert. But so there is the speed of sound changing with temperature, okay, in air. You guys have all seen fireworks and heard seen lightning and heard thunder. Okay, so here is the speed of light, 300,000 kilometers per second, and speed of sound, 0.3 kilometers per second. So light travels 1,000,000 times faster than sound. Okay, so if you see a flash of lightning, that light got to you almost instantly. And then you'll hear the thunder. Okay, so if you hear the thunder 5 seconds after you see the lightning, then that lightning was a mile away. If you hear the thunder 10 seconds after you saw the flash of lightning, that lightning was 2 miles away. Okay, so that's what that rule is. All right, so here is a diaphragm that you're oscillating. It's pumping energy into this medium, and the sound wave carries the energy away. Okay, and you want to know how much energy is being transported per second. Okay, so that's the power of the wave. So energy is propagated away from the piston by the sound wave. Okay, as soon as you stop oscillating the piston, there's no more energy being pumped in, and the sound wave dies. Okay. Well, how can you prove that sound wave carries energy? Well, you're experiencing it. So when I'm not talking, your eardrums are not vibrating. Okay. When the sound wave reaches your eardrum, it sets your eardrums in motion. Okay, so it sets your eardrum in vibration, and then that's converted into this device converts. What does this device do? The thing that's attached to the side of your head. What does it do? What? That's right. Okay, so this is a transducer. This computer of yours, all it understands is an electrical signal. So this mechanical wave that's reaching your ear has to be converted into an electrical impulse. Okay, so this guy is a transducer. All right, let me show you a more visceral example of this thing carrying energy. You guys might have heard of wine glasses being broken. By the way, go ahead and you can watch this video. The initial parts show you who can hear what frequency and stuff like that. But let's just watch the wine glass breaking. Okay, that was vibrating was the wine glass. Okay, so the trick to breaking the wine glass is you have to figure out the frequency at which the wine glass oscillates, and then you're playing the same frequency on the speaker. Okay, so that was what was happening. Okay, so here is this piston oscillating, and energy is being transported. The question is, how much energy is passing per second? And that is the power. Okay, and that's given by, so the energy being transported across the area per second is 1/2. That's the density of the fluid. That's the area of cross section of the piston or the cylinder. That's the speed at which the wave is traveling. That's the frequency, and that's the amplitude of the air molecules. Okay. And you can see the power depends on the frequency square. Okay. So the energy that passes by a given area perpendicular to the direction of travel per second. That's what that is. Okay. Intensity is power per unit area. So intensity of the sound wave is the energy being transported across a unit area per second. Okay, so intensity is power per unit area. So if you have a point source, so a little birdie singing, or you have a small speaker and it's omnidirectional. What does omnidirectional mean? So it's emitting intensity equally in all directions. Do you know any source that is omnidirectional? The sun is omnidirectional. Okay. So it's emitting intensity equally in all directions. Okay. Then the intensity is defined as the power divided by the surface area of the sphere, which is 4 pi r squared. Okay, so as you go further and further away, the intensity decreases. Okay, so if this was a birdie singing and you're standing there and then go twice as far, the intensity will be 1/4 as much. Okay. All right, so here's an interesting fact. Most people don't know this. Okay, let's say 10 violins are playing here. Okay. And now you decide that you want to hear the music twice as loud. So how many violins should play? So 10 violins are playing. You want to hear it twice as loud, and they all will be playing the same frequency and all that. How many violins should we get? All you want to hear is twice as loud. Turns out you need 100 violins, not 20. 100. Now you know why orchestras have so many violins and stuff like that. Okay. So it turns out that okay. So you want to hear it. If this is the intensity is. You want to hear it twice as loud. Now, okay. So your sense of loudness goes as this, as the power of 10. Okay. So your sense of loudness depends on x, okay, which is the power of 10. Okay, so that's why what we do is we define a decibel scale, okay, to bring this down. You take the log of the intensity and you bring the x down, and that gives you your sense of loudness. And that's how all your senses are designed as well. So for instance, if you eat something hot, let's say Thai mild, Thai hot, and then you want Thai hot, if you want it twice as hot, it needs to be, 10 times hotter. So now 10, or on the Scoville units, it needs to go from 100 to 1,000. Okay. All right. So anyway, that's how the decibel scale is defined. It's beta, the decibel sound level, is 10 times log of the intensity of sound divided by I naught, which is the threshold of hearing. This is the softest sound you can hear. Okay. So humans can detect intensities in the range of 10 to the minus 12. So this value ranges from 10 to the minus 12 watt per meter square to 1 watt per meter square. So the loudest sound you can bear to hear is 1 watt per meter square. That sound will hurt. Okay. So the intensity range, which is the energy coming at you, is 10 to the minus 12 to 1 watt per meter square. Now, the loudest sound doesn't sound 1 trillion times louder than the softest sound you can hear. Okay, so the loudest sound is about 5,000 times louder than the softest sound. Okay. So your sense of loudness ranges like that. Okay, why do you think we evolved like that? In nature, you have intensities that different. Okay, this is the softest sound you can. So you have evolved to hear this because if a tiger is chasing you, the tiger was wanting to sneak up on you. You want to be able to hear danger. Again, you don't want to die every time you hear a thunderclap, right? So you gotta. All right, so the threshold of pain, when the intensity is that corresponds to a decibel level of 120 decibels. Okay, so 120 decibels is the loudest sound you can bear to hear. Okay, and so you might have seen on TV the announcers will hold decibel meters in a football stadium and stuff like that. Okay. And the idea is, oh, this is an exciting game and that, all that stuff. The higher the decibel sound. Okay. The threshold of hearing is 0 decibels. An increase in decibels level by 10 decibel corresponds to increase in sound intensity by a factor of 10. Okay, so and remember, you had to go from, if you were hearing 3 violins, you want to hear twice as loud. What do you have to do? You have to go to 30 violins. Okay, so the intensity has to increase by a factor of 10 before you can hear. And it'll sound, sound will sound twice as loud. Okay, so here's the rule of thumb, rough rule of thumb. When the decibel level goes up by 10 decibels, then the sound sounds twice as loud. So if you're hearing a sound of 4 decibel, then 14 decibels will sound twice as loud. Okay. That's the rule. So as a rule of thumb, doubling in loudness is associated with increase in sound by 10 dB. Okay. So you go from 30 to 40 decibels, the sound sounds twice as loud. So here are some decibel levels of various things. So here's the jackhammer at 130 decibels. Okay, so construction workers, they have to wear ear muffs, because if you hear loud sounds for too long, it's psychologically debilitating. Okay, so noise pollution can contribute to high blood pressure, anxiety, and nervousness. So, and prolonged exposure to high sound level can seriously damage ears. Okay, so all rock stars have compromised hearing. Okay. And it's amazing they can still produce good music, or they can still produce music that sells. Okay. So when you hear music, when a sound wave gets to you, there's a wealth of information in that wave. It has pitch information. Of course, you can tell the frequency, you can tell the loudness, and you can tell the direction from which it's coming. So for instance, let's say here's your head and here's the sound wave. Okay, so you can tell that. This sound wave had to go through your head. Okay, so you can tell the difference between this and this. Okay. Anyway, so you can, when a sound wave gets to you, you can tell the frequency, the loudness, and the direction. So from the loudness, you can gauge how far it is, and so on, the sources. Okay. So the perception of frequency is called pitch. And you're sensitive enough where, so this sensitivity is a relative sensitivity, a 0.3% difference you can tell. So for instance, you can tell the difference between 500 hertz and 1% of 500 would be 5 hertz. A third of that would be 1.5 hertz. So you can tell the difference between 500 hertz and 501.5 hertz. Yeah. So this is, you can tell this easily. Any average Joe can do this. Yeah. So if you're more sensitive, you have a higher tonal sense, then you could do better than that. You guys have heard of some people who can hear something once and almost mimic it exactly. That's it. So they have good tonal sense. Okay. The perception of intensity is called loudness. At a given frequency, it's possible to discern between 1 dB and 3 dB. Okay. So if the sound intensity increases by 2 decibels, you can perceive the loudness difference. Okay, so the intensity is energy passing you per second per unit area. Okay. So you can have an electronic instrument measure, and it can measure frequency. You can design electronic instruments that will measure the energy no matter what the frequency is. Okay. So an electronic instrument can measure intensity irrespective of the frequency. Okay, so here's the sound level, which is a proxy for intensity. Okay, so here are the frequencies. So here's an electronic device. There's 0 decibel. At different frequencies, it can measure the energy per second and so on. 20 decibels. That's what an instrument does. This is the instrument that you are born with. Okay. Your instrument doesn't work the same way at all frequencies. Okay, so see, at 3,500 hertz, like I said, your hearing is the most sensitive. Okay, most sensitive meaning you can hear the lowest intensity sound. Okay, but as the frequency decreases, the decibel level has to go quite high before you can hear. So if you wanted to hear a 60 hertz sound, it has to be 50 decibels before you can hear it. Yeah. While electronic instrument would have detected it a long time ago, all it needs is 0 decibels. Yeah. So your ears are not equally sensitive to all frequencies. Okay. For a small range of frequencies, okay. So what we define is, so your sensitivity is defined as a phon, and an instrument's sensitivity is decibels. Okay. The relationship of loudness in phons to intensity level in decibels, which instrument detects, is shown below. The curves are equal loudness curves. So these are equal loudness curves. So you're listening to all these. All this sounds equally loud to you. So what this graph is saying is, at 4,000 hertz, 110 decibel sounds the same loudness as at 1,000 hertz, 120 decibel sounds the same loud. Okay, so that's what that's saying. And when you go to a doctor's office, that's what they're doing, measuring the range of your hearing. Okay, they'll sound different frequencies, and they'll figure out how loud it needs to be before you can hear. All right, so there's various ranges. The white area is what you can hear. Okay. So sonar is underwater communication. Here's a large rocket engine. Bats use ultrasonic waves for echolocation, and so on. Now we'll talk about interference of sound waves. Okay. So let's say you have 2 speakers like that, and this speaker sends a sound wave to that point, and this speaker sends a sound wave to that point. Okay. And let's say, or any point, if this speaker travels this distance and this wave travels only that distance, the question is, okay, what if this wave reaches with a crest and this reaches with a trough? So that wave reached that location with a crest, and the other wave reached with a trough. These 2 waves will cancel each other. Okay. So every time a crest reaches from here and a trough reaches from here, they'll cancel each other. Okay, so that will be a destructive interference. And if this wave reaches with a crest and this also reaches with a crest, then they will add each other. That's constructive interference. Okay, so so let me show that to you. Okay, so you can see that you have two sources, and what is happening here along these lines, one is reaching with a crest and one is reaching with a trough, and you have destructive interference. Along these lines, both are reaching with a crest, and you have constructive interference. Okay. So let me simulation speed damping. Okay, so I mean this kind of stuff is relevant for if you want to design a hall for acoustic engineers and stuff like that. Of course, you don't want to place seats, chairs where you have destructive interference. Okay, so for instance, so in this room when there's no chairs in the middle aisle, what that means is the speakers are 180 degrees out of phase. So every frequency is canceled along the central aisle. Okay, so that's why there's no. And if the two speakers were in phase, then you would have chairs in the middle and so on. Okay. All right, so, okay, so the point is, let's say this speaker at this location sends out a crest reaches, and if this speaker is a trough reaches that location, those two sound waves will cancel. Okay. So for two speakers that are in phase, okay, so this wave traveled that distance, and this wave traveled this distance. Okay. So the difference in the distance traveled, that's the path difference. Okay. If the path difference is an integer multiple times the wavelength, then you have constructive interference. If the path difference is a half integer multiple times the wavelength, then you have destructive interference at that point. Okay. So you have constructive interference when the two waves reach with crests. So this is constructive interference, and you will have destructive interference when one wave reaches with a crest and the other reaches with a trough. Okay. So here's a simple device where you can see interference. So the speaker is playing a pure tone, and so a pure tone is just a single frequency, and then you can move this arm up and down, and what will happen is as you're moving this arm up and down, you'll hear constructive and destructive interference. Okay, because you're changing the path. This path is fixed, but this path is variable. Okay, so as you move this up and down, you're changing this path difference. Okay. All right, now we'll talk about the Doppler effect. So you guys have heard sirens from an ambulance and a fire truck and all that. When the siren approaches you, you hear a higher pitch, and when it moves away from you, you hear a lower pitch. The ambulance is producing the same pitch. What you're perceiving is a different pitch, and that's the Doppler effect. Okay, and so you will perceive a different pitch than what is produced if there's relative motion between the source and the perceiver. Okay, and that's the Doppler effect. So let me show you a simulation. Okay, so here's a source that's producing sound. And so let's say if the frequency it's producing is 100 hertz, that means it's producing 100 crests a second. And if you're standing there, if it's producing 100 crests a second, what you'll hear is 100 crests a second. So if there's no relative motion, the frequency produced and the frequency heard is the same. Okay. Now let's make the source move toward you. So let's say you're standing here, and if the source is moving toward you, it's still producing 100 hertz, but you can see that from that illustration, more than 100 crests will pass you a second. So if a source is approaching you, then you'll hear a higher frequency. On the other hand, if you were standing here, less than 100 crests will pass you each second. So if a source is moving away from you, you'll hear a frequency less than the produced emitted frequency. And that's conversely, if the source was at rest, if you move toward the source, you'll hear a higher pitch, and if you move away from the source, you'll hear a lower pitch. Now, of course, what is this? So what is the speed of sound? 340 meters per second. So to have any noticeable effect, you got to move, at least non-negligible speeds compared to this source. To the speed of sound. So, for instance, if I ran towards a stationary ambulance, I couldn't hear the difference in pitch. But if Usain Bolt ran, he's running at 10 meters per second, he could hear the difference. All right, so if you move towards the source, you will hear a higher pitch. Okay. So here's a source moving towards a stationary listener, and this person hears a higher pitch. Okay. So here's the formula for the pitch. This is the emitted frequency. This is the perceived frequency. V is the speed of sound. Okay, so the speed of sound we'll take that as 340 meters per second, roughly. Okay. V0 is the speed of the observer. Vs is the speed of the source. Okay, so if both the observer and source are at rest, this will be 0, and the perceived frequency will equal that. So if both the observer and the source are at rest, f prime equal to f. The frequency that you hear is equal to the frequency of the source. We said if you move towards the source, okay, so let's say, okay, and by the way, so here's the sign convention. This speed is taken to be positive, okay, or this is taken to be positive when you move towards the source. And it's negative when you move away from the source. This is taken to be positive when the source is moving toward the observer. And it's taken to be negative when the source is moving away from the observer. Okay. So observer and source velocities are positive when they move toward each other and negative otherwise. Okay. So let's do it one at a time. So let's say we'll keep this 0, so the source is at rest. And if the observer moves towards the source, then this will be positive, and the frequency will be V plus V naught divided by V. This is greater than 1. You'll hear a higher frequency, okay, and so on. So you can figure that out. And this formula covers all cases. Okay. So again, if the source and observer are moving toward each other, the perceived frequency will be higher than the observed frequency. Yep. All right, so you saw that so sound waves these are the wave fronts. You can think of them as crests. Crests are high pressure regions, okay, and the gap between them are low pressure regions. So a sound wave is a high pressure, low pressure region. Okay. Now let's see what happens if, okay, what is this picture showing you? This picture is showing you there's a moving source, there's the source, and it's constantly producing sound. And a little while later, there's the source. So here's the moving object. And you can see that the sound that was produced when it was here traveled up to there, and in the same time, the source traveled up to there. It traveled outside of that circle. So this is a source that is traveling faster than the sound is traveling. Okay, so here's a source that is traveling faster than the speed of sound, faster than the speed of the wave it's producing. Okay? And what happens is, what this diagram is showing you is, see, this is the crest, and all these crests are lining up on that surface. Okay, so all the high pressure regions are lining up on the surface. And that's the surface of a cone. Okay, so if an object is flying faster than the speed of sound, what happens is, here's a cone, and the object is at the tip, and all this is the high pressure region. Okay, so what you have is, all this outside the cone is, all this is atmospheric pressure. You have a pressure spike and then a low pressure region, actually. Okay, and so you have a pressure spike on the surface of a cone. Okay, and when you hear that, when that hits your ear, that sounds like a boom. Okay, so, and that's a shock wave, and there's a lot of energy on that pressure spike. Okay? So shock waves are generated when the speed of the source exceeds the speed of the waves. The envelope of the wavefront is a cone whose half angle is given by that. So the half angle of the cone is this. This is the speed of the source, and that's the speed of the sound wave. Okay, and you can see that this equation only has a solution when the source is moving faster than the sound wave, okay, so this number has to be less than 1. Okay, the faster the source is moving, the narrower the cone. Okay. So you look at the cone shape, and you can calculate the speed of the source. And so, for instance, here's the shock wave of a bullet, and from this angle, you can calculate the speed of the bullet. Okay. So we define a Mach number telling us how fast the source is moving. Mach number is speed of the source divided by the speed of the wave. So if a plane is flying at Mach 2, that means it's flying at twice the speed of sound. Okay. The speed of sound is 340 meters per second, which is about 750 miles an hour. Okay, so Mach 2 is 1500 miles an hour. So there's the speed of sound, 750 miles an hour. Okay, so a plane actually produces 2 shock waves. The nose cone and the tail produces a shock wave. Okay, so this plane is flying faster than the speed of sound. This person hasn't heard a boom. This person has heard one boom. This person has heard both the booms. So you saw that a vibrating object will produce sound waves. So musical instruments have various vibrating objects. So stringed instruments, a string vibrates, okay? And the vibrating string will produce sound, except that sound you can't hear, it's too faint, so you have to amplify that sound. Okay? And so you have some kind of amplification device. So on the acoustic, and an acoustic guitar, the top frame, the air, they all amplify sounds of different frequency. Anyway, so here's a string that can vibrate. Okay, and so if a string is fixed at both ends, it can vibrate in only certain modes. This is the lowest frequency it can vibrate at. This mode of vibration is, the frequency is twice that frequency. This next mode is 3 times that frequency, and so on. Okay, so this string can only vibrate at certain frequencies. Okay, and the allowed frequencies are, it turns out that they're an integer multiple times this lowest frequency. Okay. L is the length of the string, and so on. Okay, so this is the fundamental mode. There's the fundamental mode. Okay, and all the harmonics are allowed. So all integer multiples of the lowest frequencies are allowed. Okay, for a string fixed at both ends. Yeah. So when playing an instrument, it's difficult to excite a single mode. So if you pluck a guitar string, you just don't excite this mode or this mode. You're exciting a combination of these modes. Okay, so you can't play a pure tone. You'd have to pluck exactly on the center, and even then you would excite this mode and the even harmonics. Okay. So it's single mode. So normally when a string is plucked, various harmonics are excited. Okay. So here is a instrument, a pipe that is open at both ends. Pipe is like that. In musical instruments, what you're doing is you're exciting standing waves. Okay, you're setting up standing waves. So when you pluck a guitar string, a wave travels there, it gets reflected, and these two waves traveling on the string set up standing waves. When you blow on a flute, when you play a flute, a wave travels like that, and then it gets reflected from the open end. Anyway, what you're doing is setting up standing waves in this air column. This is the lowest mode of excitation. This one is next, and so on. Okay. And the relevant length is the distance between the holes that you're opening and closing on the flute. Okay. So the frequencies, again, all the harmonics are allowed, and the lowest frequency is V by 2L. Okay, L is the length there. So a flute, all the harmonics are allowed. A pipe that's closed at one end, only the odd harmonics are allowed. So a pipe, only the odd harmonics are excited. So this instrument is less versatile than this instrument. Okay, because you can produce more harmonics, all the harmonics here. Here you can only produce the odd harmonics. Okay, so a harmonica, a mouth organ, is less versatile than a flute. How do you compensate for that? That's why a harmonica, a mouth organ, has several tubes. You have more tubes. Do you guys?
Trying to relate this to my experience.
What instrument do you play?
Currently the banjo.
Uh-huh.
But I've played the trombone.
Mm-hmm.
Harmonica before.
You played the harmonica?
Yeah. I wasn't very good at it.
Well, you could play it. So you see, it has it has tubes of different lengths. Okay, there are tubes of closed lengths and so on. So anyway, so in all these instruments, the higher frequencies they form a harmonic series. They're integer multiples of the lowest frequency. When you excite a two-dimensional membrane, see, the higher frequencies are not integer multiples. They don't form a harmonic series anymore. Okay. So here's a drum head. Okay, so when you hit the center of the drum, this is the lowest frequency mode that you've excited. So when you learn to play the drum, what you're doing is when you hit different parts of the drum, you're exciting different frequencies and so on. Okay? So that's what you're doing. So here's a very interesting problem. So this is quite a famous problem. So this mathematician or this question was raised. Can you hear the shape of the drum? Can you hear the shape of the drum? Meaning, so a drum is being played, and just from listening to the frequency, can you tell what is the shape of the drum, is the question. Okay. So mathematically what that means is, so different shapes can produce different frequencies. Okay. So do two different shapes have the same set of frequencies that they produce? That's the mathematical question. Okay. So this was a very famous problem, and it turns out that so Mark Cax solved this problem. He's a famous mathematician. It turns out that two different drums, see, these two shapes produce the same frequencies, have the same eigenfrequencies. And it turns out that to have the same eigenfrequencies, the perimeter has to be the same and the area has to be equal. Okay. But these are different shapes, and they have the same eigenfrequencies. Okay. When you play two frequencies that are close by, you hear a beat frequency which is equal to the difference in the two frequencies. So if you play two sounds, pure tones of frequency that are almost equal, you see that the sound intensity level goes up and down, and that's the beat frequency, and that the sound intensity goes up and down with the frequency equal to the difference in the frequency of the two sounds. So that's what, when you go when people are tuning their instruments, they'll sound the tuning fork, and then they'll match their instrument to the tuning fork. Okay. So here's a tuning, here's a pure tone. So let's say this is C, and this is a flute playing C. A C note has a certain frequency, a clarinet playing a C note or whatever. So you can obviously see the difference in the waveform. So the difference is the following. If you do the harmonic analysis or the Fourier transform, the tuning fork has a single frequency. The flute has all these harmonics, 100 hertz, 200 hertz, and all that stuff. Those are integer multiples of the lowest frequency. And there's the harmonic mixture of the clarinet. Okay? And you can see that the clarinet sounds tinier than the flute. Okay? And so this is called the timbre of the sound. Okay? Nowadays electronics are small and cheap, so you can do the following. Okay? So let's say you're listening to music on your headphones, and here's the sound that is coming in, noise coming in from the outside. You don't want to hear this, you only want to hear music. How do you cancel this sound? So since stuff is cheap now, what you do is you sample this sound, and then your electronics will produce an inverse wave. Okay, so this sound, this noise is canceled by the inverse wave. And then you can hear to your music peacefully. Okay. All right, guys.